Scenario 1 of ISEL, developed within the scope of the PAFSE project, is entitled Droplets in the Physics of Viruses Transmission. In relation to the science content from the scenario, the study and prediction of the spread of airborne particles is relevant because it can mitigate the dissemination of diseases that spread by air, thus promoting a healthier life and well-being for everyone of all ages. The analysis of respiratory particle physics and its transmission process will allow students to develop methodologies for analyzing, presenting solutions, and discussing and arguing facts about scientific problems, contributing to the interest in STEM-related subjects, STEM being science, technology, engineering, and mathematics. The scenario and the pedagogical content of the scenario allows teachers and students to explore the prediction of airborne particle spread and their relationship with public health, and subsequently present action measures in their communities to mitigate the spread of diseases. So, in this scenario, it is intended that the students analyze in a simple way how the particles spread through the air and the main risk factors to public health associated with airborne diseases. And then, with the study of how airborne viruses spreads through air, they will have to present some action measures to be taken individually and in the community to mitigate the spread of diseases. So, this scenario contains research-based activities, learning objects, interaction with animated graphics simulated, and updated facts. The scenario aims to prepare students and the school community to reduce the risk of airborne diseases, and this creation of the scenario was strongly influenced by the COVID-19 pandemic. And it is actually, in present time, it is accepted that in the scientific community that the virus spreads essentially through the air. And with the technological advances achieved today, it is possible and relevant to explore with students, a tool that in some way can predict the spread of the air or the spread of the particles through the air. And this tool is called computational fluid dynamics, CFD, which is a tool that can simulate and predict the propagation of respiratory particles in different breathing regimes and in different environments with different configurations. So in this case, in this scenario, the students will have access to simulation videos of CFD simulations where they will see particles spreading through the air, and those particles are going to be emitted in different breathing regimes when a person talks, when a person coughs, or when a person sneezes, and all these breathing regimes simulated in different room configurations. So, for instance, that we will visualize CFD simulation videos where a person emits particles in a room with or without ventilation, with natural ventilation, with rooms, tables, chairs, etc. And they will see how these objects can influence the particles spreading through the air. So this is the main context of this scenario. And the learning scenario will also increase students' understanding of how the transmission of airborne diseases work and how the STEM areas, so science, technology, and engineering and mathematics, can contribute to anticipate, mitigate, and solve public health issues like the one they are going to study in this scenario, which is airborne diseases. In terms of learning objectives that we want students to achieve at the end of the scenario, we want that students be able to describe in a global way the physical process of propagation of respiratory droplets and the respective conditioning factors. We also want that students can obtain and evaluate data and scientific data on diseases that spread through air, and they can use these facts to argue about the process of transmitting viruses by air. We also want students to be able, at the end of the scenario, to use some computational tools to build tables, graphics, and other data that aid in the understanding of the physical process behind the propagation of respiratory droplets. And finally, we also want students to be able to provide examples of factors that influence the spread of airborne viruses and can identify general measures and actions to combat the proliferation of airborne diseases. So, in PAFSE project, we have a certain number of learning resources, and for the aid of the project, the PAFSE project, we named these so-called resources in different categories. So we have in PAFSE project the so-called digital learning objects, and these are all the resources that were specifically developed within the scope of the scenarios that compose the PAFSE project, and we have the digital educational resources that are available at PAFSE Photodendron repository, and they were developed somewhat by the PAFSE consortium, and other elements of the digital educational resources are some images, texts, infographic that we research on the internet, we research on other scientific bases that would help to compose our scenarios. So we have digital learning objects that were specifically developed within the scope of the PAFSE project, and we have educational resources, which is other data that we achieved and that we collected to compose and improve our educational scenarios. And we also have a final school research project which will allow students to explore measures their school could adopt to mitigate the spread of respiratory droplets. In terms of digital learning objects, so tools that are specifically created within the scope of the scenario, in this case, we have an example of those resources, as we can see by these images, which are some of the images that students will analyze regarding the CFD simulation videos. So, as we can see here, we have 3 images at different periods of time: 1 minute of simulation, 10 minutes of simulation, 60 minutes of simulation, and we have some results. We have the particles spreading through the air in this room, and we will ask the students to analyze the particle flow, how the particles interact with the objects present in the room. So all those, so this is to give you an example of what is a digital learning object. And in this case, we can see, for example, in these 3 images, something that was developed specifically within the scope of the PAFSE project. And digital educational resources are all the scientific information that we collected, like I said, to conduct, so that students could conduct the research activities, and this is all the data that we collected from other sources to improve our scenario. So in terms of scenario and learning resources, specifically, this scenario comprises the following learning resources. So we have a repository of simulation results obtained from the computational fluid dynamics tool. And those are images and videos. So students will be able to visualize videos of particles spreading in a room with different configurations, and they will have the opportunity to see particles being emitted at different breathing regimes: sneezing, talking, and coughing. And they will also have some images at the end of each simulation from different perspectives of the room, so they can better identify the phenomena that occurred inside the room. They will also have learning guides, and these learning guides will be available both for teachers and for students. Different learning guides with adapted vocabulary for both professors and students regarding the various activities proposed in this scenario. So they will have several learning guides, also the teachers, so this will help the students analyze the various activities proposed, and also this will help teachers to better understand what we want the students developed in the activities within this scenario. So we will also have learning guides, and in this case, we will have learning guides exclusive to teachers with a detailed explanation of what is being observed in each video and the operation logic of the computational fluid dynamics tool. So this is a learning guide that we developed so that teachers can understand the full physical phenomena of particles transmission that are being observed in each simulation or CFD video. And we will also have a document explaining how these CFD simulations, our computational fluid dynamics simulations, are made for the teacher to have a better understanding of how the CFD simulation videos were created. We will also have in this scenario PowerPoint presentations on how to build and analyze a scientific document and how to build a poster. And we will also have for the several activities that compose this scenario some worksheets, including a version with answers and solutions for each one of these worksheets that students will have to develop at the end of each activity to consolidate the knowledge that they acquire in that activity. And we will also have a final suggested summative assessment worksheet that teachers can use to access or evaluate the students' work and understanding of this project. So these are all the documents that compose the Scenario 1 learning resources. In terms of class planning, we have in Class 1 a time reserved for the presentation of the scenario and the respective introductory concepts. In Class 2, we will explore the concepts of physics of airborne viruses transmission. In Classes 3 and 4, the students will analyze the CFD simulation videos of, it was said, of different breathing regimes being simulated in different room configurations. In Class 3, they will analyze CFD simulations of an initial, more simplified case study, and in Class 4, they will analyze CFD simulation videos of more complex case studies. Then, in Class 5, they will present all the data and the conclusions that they withdraw from the analysis of the CFD simulation videos, and they will debate some of the risk factors associated to particle spreading, so some of the aspects that they concluded from the visualization of the videos. And in Class 6, it will be reserved some time to conclude Class 5, and they will have a discussion of the school research project, which is the final output of this scenario of this project. In terms of scenario structure, the classes or the scenario consists of 6 classes of 40 to 45 minutes and a variable number of extra sections for students to develop their school research project. 4 to 6 sections, it can be more, it can be less. This will be at the decision of the professor, because the implementation of the scenario depends on some constraints related to specific topics according to students' prior knowledge of what is being studied in the scenario, the school curriculum, and time constraints. So the scenario was developed and was conceived to be implemented in in 6 classes of 40 to 45 minutes, but this can vary depending on these constraints that I just talked. From classes 1 to 6, students will work alone or in groups depending on the activity. This will be at the decision of the professor how students will work. And to carry out the school research project, students are divided into groups of 4 or 5. It will be necessary to use the computer or mobile phone, and it will be required that students have basic knowledge of Word and PowerPoint and some basic knowledge of English. So, in terms of class 1, in class 1 we want to present the scenario and the respective introductory concepts. So in lesson 1, students are introduced to the project and will explore in a simple way the essential concepts of fluid dynamics and computational fluid dynamics, as well as some of the potentialities of the CFD tool. And they will also debate about how to produce and analyze a scientific document. And this we will see how all these activities are scheduled for class 1. So the main objectives to achieve from the student's perspective in this class are the ability to the students in understanding how a CFD simulator can assist in predicting, preventing, and spreading airborne diseases, and they can identify factors that condition the spread of respiratory particles. So this is our main objects to achieve in class 1 and throughout all the scenario. So in activity 1 of class 1, in the first lesson, the professor should explain to the students the main objectives and the planning of the next lesson. So in this first activity, the professor should present the scenario to the students. So the following topics are covered in this activity. Students study problems related to airborne diseases through air. They will explore and explain the problem of understanding how particles of viruses airborne transmission works and how this can affect the human public health. They will seek information, scientific information about airborne transmission and research in trusted sources and share ideas with teachers and other colleagues. They will explore a computational tool that simulates the flow of particles into enclosed spaces, and they will understand the complexity of the process and identify the potential of a computational computer tool as a means to prevent and characterize and analyze this phenomenon. And they will also understand that simulators are relevant for real-life problem solving. They will understand the principle of physics and mathematical equations that explain the spread of particles. They will analyze and study results obtained from these computational tools, understand how particles flow in different environments, and at the end of the work, they will propose measures and recommendations to prevent or mitigate the spread of particles through air in the school and community spaces. So, to start the implementation of the project in itself, at activities 2, the teacher will use the PowerPoint created for this class with the name Introduction Scenario 1. So this is a learning resource, and this is a PowerPoint presentation that consists of 6 slides and contains the fundamental introductory concepts to convey to students about computational fluid dynamics and the physics of airborne transmissions. And this PowerPoint presentations was built to involve the direct participation of students. Each slide begins with a question to which students answer and inquire options of other colleagues, thus generating a critical debate on the topic at hand. As the teacher must understand what is intended to be conveyed to the students, so this will be a PowerPoint presentation that the teacher will present to students. We developed a guide called, in a PowerPoint presentation called PPT Guide Introduction, where the teacher can understand all the aspects that are introduction scenario 1. And we also have a Word document that contains the explanation in abbreviated form of all the aspects addressed in this introduction scenario 1 PowerPoint. So, like I said, the PowerPoint presentation to be presented to the students in class 1 starts, in each slide of this PowerPoint starts with a question. And the questions of each slide, it's a PowerPoint with 6 slides, are as follows. What is fluid dynamics? Which fluid properties are analyzed in fluid dynamics? Which forces act on a respiratory particle? How to relate properties and forces of a fluid? Do we need to solve the Navier-Stokes equations? How to analyze results of CFD simulations? And how to apply computational fluid dynamics to a problem. These are what we are going to see in the next slide. So, in the first slide, we have the main question, which is, what is fluid dynamics? And like it was said in this video, the fluid dynamics is the scientific area that can allow the study and prediction of how airborne transmission works. So this is the science that studies how particle flow spreads. And in a more general way, this is an area of physics, and in concrete of specifically of mechanical engineering, which studies the movement of a flow of a fluid. In this case, the scientific term for movement of a fluid is flow in space and time. And it studies the flow of the fluid by analyzing its own properties and their relations to the force which act on the fluid. And this is what fluid mechanics is all about. The study of the fluid movement, which is called the flow, and it studies the flow of a fluid by analyzing its own properties and their relations to the forces which act on the fluid. So the first main question in this slide is, what are the properties that are analyzed to study the movement or the flow of a fluid? And some of the properties the students already know, and those are pressure, temperature, density, speed, and viscosity, which is the resistance to the movement. So, in this slide, students will already have a notion of what properties are analyzed to study the flow of a fluid. So, like we saw in the previous slide, fluid mechanics is the study of a fluid flow, so the flow of the fluid, and the study is addressed by studying the properties of the fluid and the relations with the forces that act on the fluid. The properties were already addressed in the previous slide. In the next slide, we have to analyze which forces act on a respiratory droplet. And there are several forces applied on a respiratory droplet. Respiratory droplet is a fluid, so we will specify a flow, in this case respiratory droplet, for the meanings of this project, because students will analyze how particles spread through air. So there are several forces applied on a respiratory droplet, and even so, the two more significant ones, in other words, the ones that maintain the particles suspended in the air, are the gravity force and the air drag force, the air resistance force. And these are the two main forces that are applied to a airborne particle. So these are the forces that condition the flow of this fluid. In this case, the fluid is the airborne particle. So we've already talked that to analyze how fluid flows, we have to analyze its properties, its forces, and how they are related. We already saw what properties we have to analyze to study the flow, what forces are applied in this case to airborne particle. Now we have to see how the particles, the properties and the forces are connected or related. And these properties and the forces that act on the fluid are related through equations, in this case the Navier-Stokes equations, as we can see here. And these are the equations that allow to characterize any fluid's movement under normal circumstances. So, like I said, we have to analyze the properties and the forces that are being applied to a fluid, so we can describe the flow of this fluid. And these equations, and then we have to relate the properties and the forces that are being applied to a fluid. And these two aspects are related under equations, and the equations that relate the properties and the forces that be applied to a fluid, every fluid is the Navier-Stokes equations. And as we can see here, the Navier-Stokes equations have this so-called funny way and some terms that can be complex, but what we want to address the students is that they can see through here, so through these complex and funny equations, that they have the terms and the properties and the forces of the fluids presented in these particles. Because why? In these equations, why? Because I said that to study a flow of a fluid, we have to understand the properties and the forces that act on the fluid, and then we related these two aspects through equations. Those are, in this case, the Navier-Stokes equation, and as we can see, we can identify some of the properties that were previously taught. The density shown in the yellow line. We can see the velocity shown in the orange line. We can see the viscosity shown in the green line. So we can see that we have the properties of a fluid presented in these Navier-Stokes equations. And we will have the forces, we also have the forces applied on the fluid in the green rectangle. So, other aspect and curiosity about the Navier-Stokes equations is that if we simplify the equations, we can have mass times speed equals forces, times acceleration equals forces. And this equation is the so-called and famous second law of Newton applied to fluids, the dynamic law. So we can see that by reducing and simplifying, if we simplify, it depends, of course, of the problem, we can achieve the second law of Newton, and this is the dynamic law. So we can see with this scenario, this slide, that we have both the properties and both the forces characterized in these complex equations, and the relations between the properties and the forces acting on the fluid are related with Navier-Stokes equation, and this is the main idea to pass with this slide. And this leads us to the next slide, is that do we need to know how to solve the Navier-Stokes equations? As we saw in the previous slide, the Navier-Stokes equations are complex equations. And the answer to this question, do we need to know how to solve the Navier-Stokes equation, is simply no. We don't need to solve them analytically. We have to solve them to be able to predict how a fluid flow, in this case, how airborne diseases spread. But with the technological advances nowadays, a computer can be used to solve the Navier-Stokes equations through computational fluid dynamics. And this is the technology within the mechanical fluids area that can allow the development and the simulation of a certain flow, in this case an airborne flow. And you can see that in the image on the right, we can see some of the examples of the results obtained from these CFD simulations. So we can see, for example, for the image on the upper left, the airflow passing through an airplane, or in this case, an aircraft. As we can see in the image below, we can see the airflow streaming down and up a Formula One car, and these are some of the examples of how we can use computational fluid dynamics to predict the flow of a certain fluid, in this case the air. And we can also see in the two on the right, the upper right and the below right, that we can see some of the images that we had to create to simulate how airflow and airborne particles circulate inside the rooms of the CFD simulation videos that students will analyze in the next classes. So the main idea to pass with this slide is to transmit to the students that we have we have Navier-Stokes equations to relate the properties and the forces that act on the fluid to predict how the fluid, we have to solve the Navier-Stokes equation to predict how a fluid flows. And we don't need to solve the Navier-Stokes equations by hand, so analytically. We can use a tool, in this case a computational fluid dynamics tool, to simulate, to solve the Navier-Stokes equations and to analyze the simulation results, in this case the particles spreading through the air. And then this leads us to the next questions, which is how to apply computational fluid dynamics to a problem. So, so far we saw that the properties to study and predict how a fluid flows, in this case how airborne particles flow through air. We have to analyze the properties of the fluid, the forces that act on the fluid, and how those two aspects relate with each other. We saw that we need equations to relate properties and forces, and in this specific case, we need to solve the Navier-Stokes equations. These are complex equations, and we don't need to solve them analytically. We can solve the Navier-Stokes equations throughout a computational tool. This computational tool is called computational fluid dynamics. And now, how to apply computational fluid dynamics to a problem. In CFD work, boundary conditions are parameters which allow the computational tool to properly simulate the flow of a fluid in a certain physical space. So, like we saw, we have to solve the Navier-Stokes equations to predict the flow of any fluid. But I can have water, for example, running through a tube. I can have honey, for example, or oil running through a tube. And the Navier-Stokes equations are always the equations to be solved to analyze and predict how the fluid flows. But as we can see here, I just mentioned three different fluids, honey, water, and oil. And all these three fluids will have different properties. So, in my computational fluid dynamics tool, I have to identify specifically what are the fluid properties of the fluid that I'm simulating, so that the Navier-Stokes equations can be adapted to the properties of that particular fluid. I also have to identify which forces are applied to a fluid force. For example, in the case of the airborne particles, we have gravity force and air drag force. So this needs to also be mentioned in my computational tool. So my computational tool knows that she will have to analyze and solve the Navier-Stokes equations, but the computational tool requires information about what fluid that we want to simulate and what forces are applied to that particular fluid. And then, for example, I can simulate how water runs through the tube, but I can also simulate, for example, how the same water runs, for example, in the ceiling or runs in stairs, for example. So we will, besides the fluid properties and the forces applied to a fluid, we will also have to simulate to my computational fluid the physical space where this fluid is being simulated. So we have to describe the physical space characteristics to my computational fluid dynamics tool. In this case, these characteristics can be the wall temperature, For example, for instance, if we have an HVAC system installed, we have to signalize to the tool the amount of air in the diffuser, the amount of air coming in through a window. So all those aspects have to be mentioned in my computational fluid dynamics tool, and all those aspects are called the boundary conditions, which are the characteristics specifically associated to that fluid flow. The fluid properties, forces applied to that specifically fluid, and the physical spaces characteristics of on where that fluid is being simulated. Now, and to conclude this scenario, this slide, we have a certain summary board to consolidate this knowledge. So the students already know that to study the flow of a fluid, we need to know the properties of the fluid and the forces applying on the fluid, and those two aspects are connected through the Navier-Stokes equations, which can be solved through a computational tool called computational fluid dynamics, which needs boundary conditions, which are the properties of the fluid, specifically fluid, the forces applied on that specific fluid, and the physical space characteristics on which or where which the fluid flows in. So this is what we want to achieve with this PowerPoint presentation in this activity. And at the end of this class, we want to give important feedback to students on how to search for credible information to conduct research work on a new PowerPoint presentation. And we have a new PowerPoint presentation entitled How to Write and Read a Scientific Document for this instance. And this PowerPoint was created and this can be used by the teacher to explain to students the way of how to analyze and to write a scientific document. And fundamentally, this PowerPoint presentation, how to read and write a scientific document, is divided into parts. The first one exposes the sequence of how to read and analyze a specific scientific document, as well as to focus on useful information. And the second part intends to convey students step by step on how to build a scientific document from scratch. So this is the main idea, the activities that we want to develop in class 1, and in class 2 is an hands-on activity on the physical process of airborne particle propagation. So this activity serves to consolidate the knowledge that students acquire in class 1, and this activity is called Explore Concepts of Physics of Airborne Virus Transmission. So if the teacher has not completed activity 3, so the presentation of that PowerPoint presentation on how to analyze a scientific document, the teacher can use activity 1 of class 2 to conclude the presentation. Then the teacher proposes to the class an activity that aims to analyze and explore and deepen the knowledge and consolidate the knowledge that students acquire in class 1. So students should be divided in groups of 4 or 5, and the distribution of the proposed worksheet for this class will be made. And this worksheet is based on three questions. The first one, the students must carry out an autonomous research on the physical process of transmission of airborne diseases, airborne particles. In the second, they have an interactive crossword puzzle to fill in with concepts taught in class 1, whereas the third question is a multiple choice question where they will need to carry out a research activity to correctly answer, since it relates to the dimension of a respiratory particle. So basically, this worksheet was created to consolidate the knowledge of the students, knowledge acquired specifically in class 1. And as already mentioned, a possible worksheet solution is available for this sheet. So in them, with students having already a theoretical knowledge of how airborne particles spread through air, they will start analyzing the CFD simulation in class 3 and in this case they will analyze the CFD simulation videos of an initial case where students will, through the analysis of simulation results, observe the influence that the variation of parameters that characterize the process of propagation of respiratory particles has on their behavior for different breathing regimes. And then students will perform the practical activity of consolidating knowledge acquired during the class. So, in this case, we have several materials to be employed in class 3, and those materials are 3D CFD simulation videos of airborne particles propagation emitted in 3 distinct breathing regimes. So they will have 3 different simulation videos where they will see a person speaking, sneezing, and coughing through time. They will also have images from different perspectives of the room at the end of each CFD simulation to assist students in interpretation of results of the respective simulations. In this class, we will also have available a PowerPoint exclusive for teachers with a detailed step-by-step explanation of the configuration of the videos and the phenomena observed in each video, and a learning guide for both teachers and students as the follow-up and the explanation of how the video should be analyzed, so the several step-by-step activities that students should fulfill to analyze correctly the videos, and how they should fill out the worksheet proposed to be filled in the end of this class. And we will also have for the materials of class 3 the worksheet of this class. So in terms of video organization, as mentioned in the learning guides, as you could have the opportunity to address in the future, and in the Word document, for each situation that students must analyze, 2 typologies of videos are available. One in which only the first minute of the simulation is available, and the second one in which the entire simulation is observed. Each simulation was conducted for a total time of 60 minutes, so they will see in each video the particles spreading through time during 60 minutes, and the simulation time can be observed in the upper left corner of each video. In the lower right, will also have a contained color caption which represents in meters the size of each particle emitted by the emitting occupant. And the scale ranges from 1.10 minus 6 meters to 1.10 squared minus 3 meters in orange color. So the bigger particles are represented in red or orange, and the smaller particles are represented in blue colors, as we will see in the videos. So, like what I said, the students will have 2 typologies of videos. One in which only the first minute of the simulation is available at a lower speed, as students can have a better understanding of how particles spread through time, and they will have a second typology of video where they will see the entire simulation observed. The first minute with a lower speed, and then the following 59 minutes with a more speedy velocity. And then the room where each breathing regime was simulated is the same for the cases of class 3. So they will see 3 simulation videos, one where one person coughs, one person sneezes, and one where a person sneezes, talks, but these videos were all simulated in the same room, the same classroom, except for the absence of a ventilation system in the case where the person speaks without a ventilation system. So in these 3 cases, the case where a person coughs, sneezes, and talks, these 3 cases have a ventilation system on the room. And they will have another case where they don't have a ventilation system, so they can compare the influence of a ventilation system in and without, in or out of the room. So as we can see here, we have the classroom layout. So we have a classroom with 6 rectangles on the ceiling, which are the lamps. two squares on the floor, which are the air diffusers, and these four representations here, which are the occupants, the column cap in the below right side of the image, and the time of the simulation at the upper left of the image. So this is the main classroom layout from class 3. So the video is only with the first minute of the simulation, and this structure, and I will follow to, I will pass the video. So as you can see, time is clocking. We have the particles spreading through 60 minutes, in this case 60 seconds, 1 minute, in this case the person, one, only the occupant 1 is speaking, and we can see the particles spreading. And now I'm going to show you the case where a person sneezes. So we can see how particles spread through time during 1 minute. So this is the first typology of video. The video where students will only see the first minute of simulation. And then we have the videos with the entire time of simulation. So in the case of speaking regime, we can see here that in the first minute the particles have the same velocities of the videos with only the first minute. And now we can see that the video is going to accelerate through the next 59 minutes, as we can see the particles spreading through the air. Some of them are being removed by the ventilation system. So this is the main aspect of what students can analyze. I'm going to pass the sneezing regime. Note that, for example, the speaking regime, a person is talking during 5 minutes, so particles are being continuously emitted throughout 5 minutes, and in the case of sneezing, we will only have one act in which a person sneezes. As we can see, we have particles being removed. So these were to show you the two main typologies of video that students will have at their disposal. And then they will have different pictures of different perspectives of the room at the end of the simulation. In this case, we have 3 different perspectives. One where we can see the room in the diagonal perspective, one where we can see the room from the ceiling perspective, and one when we can see the particles around a certain occupant. So these will be images that we can help students analyze, better analyze the results obtained from the CFD simulations. They will also have some pictures of the flow lines. These lines, as if you are recording, are similar to the lines that we can see, for example, passing through the simulation of an airplane or passing through a Formula One car. In this case, we have the flow lines that are described and that are originated with the flow of air created inside this room. So in this activity, at the beginning of the class, students should be divided in groups of 4 to 5 to analyze the videos. For each situation mentioned, the room as a ventilation system, so to establish a point of comparison, students will also analyze a situation, like it was called, in which a person speaks, but the room has no ventilation system. And subsequently, for starters, students analyze the videos from the first minute of the 4th situation. Person coughs, sneezes, and speaks with ventilation system, and the person speaks without ventilation system, in which preferably the situation with and without ventilation should be analyzed next to another. And they will have to analyze, and if they analyze the video in which the occupant speaks with ventilation first, the next video to be analyzed should be the one in which occupant 1 speaks without ventilation. If necessary, students should regard the images from different perspectives of the room to help them better understand what they just observed. And then each group answers the worksheet developed for this lesson. This worksheet consists of 5 questions, and after filling the worksheets, students should also prepare a small scientific report that summarizes the main results observed in the videos of the CFD simulations. And this activity can be performed, for example, as homework for class 4. These are the main questions that the worksheets F. So these are questions related to some aspects in the phenoms that they observe in the CFD simulation videos. And then we have a specific note to better improve the dynamic of this activity. And these are some counsels that we leave to teachers to develop to better dynamize the activity and to respect the proposed time limit for the class 40 to 45 minutes. So, for example, students should already have access to the videos and images before, prior to the class 3. It's important that they all have already read the learning guides to the study method class 3. The classroom should be prepared and the tables should be already arranged for group work before the students come in. These are some aspects that, if they are implemented, this will help respect the proposed time limit for the class. And then these were the activities developed for class 3. And then in class 4, students will analyze CFD simulations or more complex case studies. And in this case, they will analyze propagation of air through time in the same room, but a room with more objects and more complex geometry, as we will see in the next slide. So for the materials of class 4, we have the same materials for class 3, the 3D simulation videos with two typologies, one where they will see the first minute of the video, another where they will see the whole simulation through the 60 minutes, images from different perspectives, the PowerPoint exclusive for teachers with a detailed step-by-step explanation of the phenomena observed in each video, learning guides for students and teachers, and the worksheet for class 4. And in this case specifically, students will have to analyze only the situation where a person speaks in different room configurations. In this case, 3 different room configurations. Because in class 4, we want students to analyze how different room configurations can influence the particle spread. So in class 3, they saw how different breathing regimes can influence the particle spreading. In this case, we want them to analyze how different room configurations can influence particle spreading. So we have 3 different room configurations. One where we have the diffusers on the floor. We have, as we can see, more complex humans with more complex geometries. Each one have one table, one keyboard, one tower, one monitor. So we will have more objects, and in this case we have simulated a room context in which persons are working in a room. And so the standard case is a standard because it has the same ventilation system as the cases analyzed in class 3. So we have the diffusers on the floor and the extractor of the air on the ceiling. And then we will have another room configuration where we have the ceiling totally installed on the ceiling, or the air conditioning totally installed on the ceiling. So we have the diffusers on the ceiling and the extractor. And we have a room configuration where we only have natural ventilation system. So we don't have mechanical ventilation. We have a bridge through a door where the air can come out, and 2 bridges in the windows where the air can come in. So air comes in from the windows and can come out from the bridge on the door. And this is the case where they will analyze how particles spread in the natural ventilation environment. So in this case, students should, like in class 3, students should be divided in several groups of 4 to 5 and should analyze the videos with the same methodology of class 3, and they should fulfill the worksheet available for this class. And for a complementary activity to reinforce students' knowledge, we will have a complementary activity to be developed, for example, outside the class. this is not mandatory, in which it is proposed that students analyze the simulation of sneezing in coughing breathing regimes from standard cages with a ventilation system fully installed on the ceiling and with a natural ventilation system, which means that we propose in the complementary activity that the students analyze all the breathing regimes in all the different room configurations. This is obviously difficult to do in 40 to 45 minutes. We only ask that students analyze the flow in the situation where a student, where a person speaks in different room configurations, but in this complementary activity, professors can address all the breathing regimes. So in this case, we also have the important note of some advice to dynamize the activity, just like in class 3. And finally, at class 5, they should present the results of the worksheets of class 2, 3, and 4, including the scientific report made in classes 3 and 4, and it should be organized as a debate where students, based on evidence, they verify the analysis of the simulations and what they studied in the first classes. They propose measures to combat the spread of airborne diseases. So, at the beginning of the class, students should present in groups the answers to the questions of worksheets of classes 2, 3, and 4. A time limit is established per group and is mandatory that each element of each group talks at least once, because one of the main goals of the PAFSE project is also to encourage students to be able to talk in public of some scientific issues. While a group is presenting, the teacher tells the other groups to write down the main differences between the answers they gave and those from the group that is presenting. In this activity, a debate should be created in the class, and in first instance, the different points of view among the students are discussed in relation to the worksheet's responses, and in the second moment, it is intended that students debate and produce conclusions about the main risk factors associated with the spread of diseases by air and what measures, general and individual, the students would apply to mitigate the spread of diseases. So, some questions to address the first topic the teacher can ask the class, which the students will have to answer, arguing with what they answered in the worksheets. These are some suggestions to questions that the teacher can have with their students. And in the second part of the debate, the teacher lists a series of questions to which the students answer based on the worksheets, the scientific reports, and what they learned in class 1. So these are some suggestions to questions that teachers can have to their students in the second part of the debate. And the main focus of the debate should be the general measures that students will select to apply both in community and the individual level to mitigate the risk of spread of diseases by air, using what the scientific argumentation that they produced with the scientific reports, with the questions from the worksheets 2, 3, and 4, and from the videos from the aspects they analyzed in the videos of classes 3 and 4. The teacher should divide the groups in 4 or 5 students. Each group is given a time to communicate a set of proposals on how can we mitigate the risk of transmission of viruses by air through the influence of individual behavior. And the rules of the debate should be defined by the teacher, but each member of group must speak at least once, and the order on the context of the intervention is previously discussed by the group members. In terms of class 6, so this is what we have defined for class 5, the debate and the discussion about the results that students produced in the worksheets and what they analyzed in videos of classes 3 and 4. And then in class 6, students should conclude the debate, because this can have some activities to to develop in class 5, so we have some space of time in class 6 reserved to the conclusion of class 5, and then the debate on the general measures to be applied to mitigate the spread of airborne diseases should be conducted, and the theme of the school research project is discussed in class 6. So, in activity 2, in the second activity of class 6, the teacher uses the PowerPoint presentation entitled School Project, How to Make a Poster, to present the school research project to the class. So, in this case, the school research project is the final activity from this project, the PAFSE project, in which each group is challenged to create a poster that contains images, texts, infographics, graphic representations, with the conclusions the students drawn from the analysis of the case studies and what they achieved in the several research activities conducted throughout the scenario. So students are encouraged to revisit the scientific articles they have consulted in the research process to explain the results of the simulation, and based on this information, elaborate some proposals to mitigate the airborne diseases spreading through the air. So with the information that they acquire with the study of the scenario, they should produce the proposals to mitigate the airborne diseases spreading, and they should implement these proposals in the form of a poster. The best format for the presentation of the results, the project results, should be discussed, and the notes made by the groups throughout the implementation of the scenario, which are measures, justifications, filling out of the worksheet, how the poster should be created, should be discussed in class 6. And then, to address this PowerPoint specifically, this PowerPoint contains some examples of successful posters, as well as the main guidelines to follow to create a good poster. This document also contains an explanation of the general objectives of the school research project, as well as a tutorial that students can follow up to set up a PowerPoint slide in the dimensions for which the poster will need to be created. And then, to complement the implementation of the project, the teacher also has at his or her disposal a summative evaluation form that summarizes, consolidates the knowledge acquired throughout scenario 1. This is a worksheet that teachers can use at the end of the scenario to evaluate as an element of the evaluation of the project if they so wish. And this worksheet, like others, also contains a version with the solution, with the answers for the proposed questions. And then, for the school research project, to address the school research project, like I said previously, based on the knowledge acquired in the previous classes, students are encouraged to revisit the scientific articles they consult in the research process to explain the results of the simulation, and based on this information, to elaborate their proposals to improve public health. These proposals will be presented in the form of a poster and scientific presentation. The project should be carried out in groups, and during the project, the teacher must act similarly to the other classes. That is, they must circulate around the room and collect feedback on the students when they are carrying out the activities and supporting them whenever necessary. And this project is also wanted to be multidisciplinary. That is, the arts teacher, for example, can also help the coordinator professor of the project in the design and creativity of the scientific poster and infographic. The ICT teacher can help students, for example, in the creation of the scientific presentation developed in PowerPoint, for example, and for example, the languages teachers, Portuguese, English teachers, can now help in the proofreading of texts produced in both outputs, both the scientific presentation and the poster or on the infographic.